Hello, everyone. It's a pleasure to be here to be presenting on reproducible pipelines for neuroimaging research. So first of all, the disclosures. The first thing to disclose, all the code and data for both the slides and the content supporting the slides are available in this QR code. I would highly encourage you to scan it and or find it in our provided material and open it in your laptop, because then you can follow along in the interactive notebook that is provided, which contains example codes, particularly for the latest section of this presentation. I also need to acknowledge that I personally have a positive bias towards open science practices, so some of what I say may or may not resonate with your point of view, but I completely acknowledge that, and that's not a problem. And I'm also a developer of one of the tools that I'll be presenting or mentioning throughout the talk, so I need to acknowledge that I might be biased towards that. And finally, I need to mention that AI was used to make the content of the slides shinier, but I can assure everyone that all the final edits were reviewed by me, and everything that you see reflects my voice and intent. Hopefully anyone who needed to scan that QR code has already done that. And one final thing to acknowledge, I am notorious for going over time on slides, so I probably will speed up at points throughout the presentation just to make the time. Thankfully, the previous speakers gave me a few extra minutes that I can use. So what are we going to talk about today? We are first going to talk about why reproducibility matters, and then the talk will basically divide into two sections. First, we're going to talk about reproducible analysis pipelines, so taking small steps to make our code more reproducible, and that's basically talking about coding best practices and why Jupyter notebooks are an effective tool to help. Then we'll move on to reproducibility in the context of neuroimaging visualizations and scientific visualizations in general. So we'll talk about the idea of programmatically visualizing stuff, and we'll mention a range of visualization tools that will help us do that in our real-world research practical lives. Anyway, so with all that said, why should we even care about reproducibility? So science does build on science, and without reproducibility, findings are hard to be trusted and may not even be replicated. Neuroimaging findings in particular are usually often results of complex pipelines, and that makes the scenario worse. So we certainly need to ensure that what we do is reproducible, because without access to code, even small analytical differences between pipelines could cause big differences down the line in terms of the findings of the study. And what is at stake when we're talking about making our research reproducible, or what's going to happen if we don't? I really like this comment by a professor of statistics from Columbia University that says the authors of the research paper don't have to provide their data and code, and I have no obligation to believe anything that they say in the paper. So I kind of do lean on agreements with this comment. I generally have a positive bias towards papers that do provide their code and data. So it kind of improves the credibility of research, I think. And I'm sure, just by a raise of hands, how many of you had to replicate something from a previous paper and found out that there was no code available, so you ended up spending a lot of time? Okay, so at least those of you know what I mean. And also to point out the other side of the spectrum, have you ever wanted to replicate something and came across a paper that did have the code and data ready? A raise of hands. Oh, good, good. More hands. So we are doing great in that sense. Another point that is at stake is the impact of the research. So as I said, if people don't see your code, they might be less persuaded to try and expand on your earlier work. So now that we kind of mentioned why reproducibility matters, let's talk about how we can improve our code an analysis mainly, because there are different types of reproducibility, and most of what I'll be talking about today is about the pillar of analysis pipelines and code. So the two main topics that I'll be talking about in this sense will be about how we could make our pipelines, which are actually the analytical steps that we take in our research, to be more reproducible, and how we make our visualizations, which is kind of the face of our research, more reproducible. So on the pipelines, I'll basically go over a range of best practices. So the goal is to show simple steps that we can take to make our code easier to reproduce. And along the way, I will introduce some tools that may facilitate continuous and seamless code sharing as we do our research. So first and foremost, let's address the elephant in the room. Many of us, including myself, whenever we're thinking of providing our code openly for others, are always worried that we're going to be judged based on a typo or a mistake or something that is lying there in our code, and we may not be aware of it. And I'm basically here to say that there are simple, effective ways to boost code quality, so very small, tiny steps that make big differences, and won't take that much effort or time from us to implement, and that will hopefully help us resolve this anxiety of sharing code. And I should also say that these days code sharing is no longer a luxury, it's increasingly expected in our community, and with that comes the idea that code doesn't need to be perfect. So people understand that you have made an effort to make your code public, and it's understandable that, as other aspects of science, code sharing itself can also have flaws, and that's why we can build on our openly available code. So any effort to share code is generally better than no code sharing at all. So what are those small steps that we can take? So I'll basically go over a few simple things that I think are keys to making our research code easier to share openly. The first idea is commenting, and it's basically saying that we need to use comments to make our code more understandable for those other humans that are going to use it. It's usually not expected of researchers to provide documentations for their analyses unless they're like providing a software tool, but no matter what research you do, if you're providing code, it's a good idea to leave some comments here and there in your code so that people would understand what the script is doing. And basically comments are essential if you want to make your code shareable and reproducible. Now the question is, where should I place comments? There are basically two main areas of your code that you ideally should place comments in. There's the top level script comments. This is basically if you're writing functions, it's like the doc string that you put in the function, or if you have different files for your script, there should be a usage kind of comment, multi-line comment at the top of the code, and it usually should contain at least one example of how others could use that script. And the other place that would require code comments is generally inline comments. So whenever you're doing something in a stepwise manner, it usually helps to explain what those steps are with like one-liner comments. And it's also good to say that comments is not just for reproducibility, it also helps your future self down the line. I have experienced this multiple times that I had to read my own code after a year or two, and if I didn't have commented it, I would be like confused for like a few days just trying to figure out what I wrote down like a year ago. So comments help yourself as well, make sure to do it. Then there's variables and how we use variables in our code. Basically, the idea is instead of putting hard-coded things like paths to a directory or a parameter like a p-value or a threshold, it's better always to define some variables at the very top of your script so that people could, if they want to alter your variables, they could do it. And yeah, it kind of centralizes those parameters so that people know what parameters your script take, and they could change it when they want to use it. So basically, to give you an example, instead of having a code that looks like the one on top, which is basically has a hard-coded value, even if it's a p-value of 0.05, which is commonly used, it would be better to have some section at the top of your code where you define this parameter, and then later on down when you're using it, you just refer to that variable that you've defined on the top of the script. The next point is use of functions. It's generally good to use functions in your code. Functions are basically blocks that make your code more modular and help you in terms of not repeating something multiple times within your script. And as a good rule of thumb, if you have something in your script that is repeated more than twice, that's probably a sign that it could become a function. And it's also good to point that good functions are usually not too long. So let's say 20 to 40, 50 lines of code. If you have a function that is, I don't know, 1,000 line of code, you're probably better off breaking it into smaller functions. It will become easier to track what that function is doing down the line. And the other point that you need to take into account is that you need to eliminate duplications in your scripts. So what does that mean? Well, it has two aspects. When you're writing your own code, use functions to avoid copy and pasting stuff here and there. And also notice that it goes beyond your script. So there are times that you could use code that other people have written in order to avoid reinventing the wheel. And not only will that make your code shorter and easier to read, it will most likely make it more efficient, especially if you're using well-established tools and packages that do something. So say if you want to compute a Pearson correlation, you don't have to hard code the formula for that. You can use a package that does it. The other thing to take into account is how you name your variables. And it's always like a point that takes like a lot of time to decide, like, oh, do I use something that is really short and easy to rewrite later on, or do I make a long variable name that is more informative and descriptive of what I do? And the general recommendation is, unless it's something that is really intuitive, let's say like an index I in a for loop, everything else is better to be descriptive. And these days, given that we have tab completion support in many text editors, having a long variable name doesn't really mean you have to spend longer time coding. You just start typing the name and do a tab, and the magic does the completion. So yeah, use descriptive variable names wherever you can. And then comes the issue of dependencies. It's always good practice if you want others to use your code to have a file that basically explains what are these other packages that your tool uses. In Python, it's usually either a requirements.txt or a YAML file that helps pip or conda understand how to initialize an environment to run your code. And an alternative is to also provide a getting started README in your, assuming your code will live on a Git project, a Git repository somewhere. It's good to have a getting started section in your README that you briefly describe how someone else can use your code and if they need to do any additional setups like a virtual environment or a Docker container for that. And finally, another point that you need to consider is commenting is good, but commenting out code in order to skip doing something for now and let's see if later on we can configure that is not a good idea. So I myself am guilty of doing it from every now and then, but it's a good practice not to comment out your actual script. And if there's a moment in your prototyping that you want to turn off a functionality, it's better to use an if-else statement to basically say, okay, I have a comment, this bit of code I don't want to use right now, and then there's an if-else statement saying, like you put a flag there and the code skips that section. That's usually a better practice than commenting out code in general. Then there's the idea of archiving your code, and this is really relevant in the context of research because this way you can not only share your code, but make it citable and referenced. So there are tools like Zenodo, as Stefano mentioned earlier, that do link well with a GitHub repository, and it's easy to generate a DOI for your code. So not only will your papers attract citations, but also the code that you provide for others to use. And finally, while a lot of software development packages may require scripts of code, there's this other solution that works really better for those of us that are that basically need to provide our code publicly, but it's not really going to be a software package, it's just a script for people to use, and that's Jupyter Notebook that can help us. So basically, when we have a Jupyter notebook, we kind of avoid the overkill or the barrier of creating a proper software package for others to use our code. And in the next section, I'll basically describe a few pointers on how we could use Jupyter efficiently to make our code available to others. So the idea is that as soon as you start your research, so it's not at the point that you're publishing the paper, but as soon as you start your research, you create a directory where your code and data for that specific project lives. And in that directory, you initiate a Jupyter environment. It's synced with GitHub, so you know how you're tracking things over time. And you basically back up everything. All the analysis is on Git. And once the paper is ready and finalized and you want to publish it, you can simply turn a private Git repository to a public Git repository, and everyone can at that point see a version of your code that is working. And the good thing is that Jupyter nowadays comes with support of a lot of different kernels. So no matter if you're an R developer or a MATLAB developer, you still can utilize this functionality. It's not specific to Python, and no matter what language you use, you can still benefit from the Jupyter Notebook environment. And an advantage of these Jupyter Notebook is that they're linked with GitHub in a way that GitHub renders web pages for you when you have these notebooks. So not only will you have code that people can use to reproduce your findings, people can essentially see the output of your code in a website without you doing any additional steps, which does give a lot of credibility to research findings. And here's like a general recommended directory structure to begin with. If you're looking for like a simple template, essentially you would have a project directory where your all the data and code related to a single research project sits. And inside that, you'll have a notebooks directory with different subdirectories for the steps in your analyses. And there you'll have different notebooks explaining whatever is happening in each step. It's a good idea to include the readmes both in the notebooks directory, but also in the project directory to basically explain how people can use what's available in those places. And it's also, as you can see here, there's the possibility of having a data folder that could possibly be linked to things like DataLad for access. You could have a different folder for documentations if you like, but that's not a necessity. And finally, it's good to include that environment.yaml or or requirements.txt file that basically explains how people can set up an environment to run your code. Now, another good thing about Jupyter Notebooks is that they also support narrative storytelling, so it's not just code. You can explain there what each section of your code is doing and divide it into cells so that if someone is checking your scripts, they get a sense of what everything has to do, and it also gives some sort of separation between different steps in a notebook. And it's generally recommended to avoid creating large notebooks that are like hundreds of megabytes. There are ways to push those into Git, but it's easier to see notebooks that are smaller in size. So it's a good idea to break your notebooks into chunks that have a manageable size. And if you have to run an analysis that requires a notebook of larger sizes, you can use Git's large file storage to handle that, but generally it's recommended not to do that. And with all that being said, I want to move now towards the idea of reproducible scientific visualizations, which has become a passion of mine in the past couple of years. So in the next section, I'll talk about the importance of making visualizations reproducible, and cover various resources and tools that support reproducible scientific visualizations. I need to highlight that if you have the interactive notebook loaded, this section also does come with a Jupyter notebook with example codes that essentially provide some neuroimaging visualizations all through scripts. So you can feel free to try them now. Let me know if there was any issue, and feel free to use it in your own research if you'd like. And I will also provide a set of concrete practical examples in those notebooks that you could check. Before starting this section, I have to acknowledge that it was quite a while ago, maybe 6 or 7 months ago, that I was sitting in this talk by Dr. Sid Chopra, who actually, like a lot of the things that I'll be talking about today comes from that talk. It was really insightful for me, so I thought it's worth the acknowledgement. Thanks to Sid for helping in terms of providing some of these contents, but make sure to check out. I think he has a paper. I have a reference to that paper in the website that comes along with these slides. Make sure to check out that paper. It's on basically different visualization tools that we currently have for neuroimaging research. That being said, let's talk about why visualizations matter. And I'm going to start giving you a story of my own. So this figure here is a figure from a research in 2014 that was basically done to show how psychedelics affect brain connectivity. And I remember back then I was like an undergrad student in electrical engineering. I had no idea about the brain. I did not read neuroscientific literature at the time, but I did listen to TED Talks. And I remember like seeing this, and ever since I remember that this picture sort of stayed with me all along the process. And these days, I went back and I noticed that this single figure was actually showcased in multiple TED Talks. It made itself into news. And that's kind of an example saying that although we spend a lot of time writing our manuscripts, sometimes the figures make it to bigger places. So this figure is an example of a figure becoming the public face of a study. And it's a pity that the original image is not completely reproducible, given that back then it was not commonplace to provide scripts that others could use to reproduce your figures. But we've fortunately evolved since then, and visualizations in sciences has become more common to be reproducible these days. And that brings me to the topic of GUI-based versus code-based visualizations. Now, this is supposed to be an animation if you are checking the slides online, but here it's just a picture. So GUI-based visualizations is this idea of you open your favorite GUI, let's say it's the Connectome, Workbench, or FreeSurfer, or whatever other tool is. You load the files that you want in the GUI, you make them look the way you want, and then you take a screenshot. It has its place, and it's really effective in terms of like making everything look the way you want, but the problem is for someone else to reproduce that same figure, it's nearly impossible. Now, code-based visualization is this other side of the code where the other side of the coin, where instead of doing the GUI-based thing, you just write a code that loads your files and puts it into a nice figure for you. And the benefit of doing this, although it takes some time to set up, is that anyone else can essentially remake the figure with the scripts that you use to make it. And that's why we'll be talking about code-based visualizations now. So what are the benefits of doing code-based visualizations? Obviously, the first thing is reproducibility, and that's why it's covered in this talk, but it goes beyond reproducibility. And so another benefit of doing code-based visualization is that it is more flexible, so you can seamlessly tweak styles. Let's say if you're not happy with a particular color map, you're not happy with a particular angle of viewing, you can easily change those in the code, and it takes a second to run again. And it's scalable, so if you're generating not just a single figure, but 10,000 figures, or like you're making an animation, or doing like a QC that requires several figures to be generated, then That's another benefit of using code-based visualizations. It can also become interactive, so alongside your paper, you could have this website that hosts an interactive visualization of your research that people can like use to rotate the brain, let's say, and find and see the effect that you're putting in your manuscript in a more interactive way. It also supports automation, so you can integrate your visualizations into your analysis pipelines. And let's say if you have a multi-panel figure for your manuscript, you can automate it to be generated all by code. No need to like manually go to Photoshop and add things here and there. And another benefit of it is that the skills that you make, while you may have it may have a steep learning curve, it stays with you. So the figure that you made 5 years ago, if you have the scripts for it, you can remake it in seconds. If you don't, you probably need to sit down on the computer, try to figure out what you did 5 years ago to be able to make something similar to that. Now, with all that being said, let's now introduce some tools, libraries, and templates that can facilitate code-based visualization and share some example code in the Jupyter code that you already have access to showcase these visualizations. So let's first start with a range of general purpose visualization tools that can help in any type of scientific visualization, and then move to neuroimaging specific visualization libraries after that. So in terms of general visualization, there are some basic plotting libraries in Python that you might have heard of. There's matplotlib, and then there's Seaborn, and together they have a gallery of all sorts of different visualizations that you come and see across papers. But if you wanted, so some of the advantages of these tools is that they have features that are useful for making scientific visualizations, such as making multi-panel layouts that are helpful to make figures. They give outputs in all sorts of different formats and resolutions, so it's easy to make something that looks nice in your manuscript later on. It supports LaTeX, so you can add equations in your scripts if you want. And finally, it links well with tools like NumPy or Pandas, so data that you load in your code is easily integrated to your visualizations. And beyond those simple tools, there are tools that can help you make interactive visualizations. So there's Plotly, which is one of those tools that provides ways of making visualizations that are not static and you can interact with the cursor or the keyboard. There are a bunch of other tools that also do something similar, so it's worth checking those out. That's why I left them here. There's also the idea of using these visualization data shaders that are helpful when you're dealing with large amounts of data. So if you, let's say, want to visualize 1 million points, normal visualization libraries could not handle that and may take a really long time, but there are packages like Data Shader that help with visualizing plots that have large number of elements. So this could come in handy in our context of neuroimaging, particularly when we're studying dynamical systems and we want to essentially render how the space of the latent space of these variable changes look in a dynamical system. Then there's the concept of using the right color maps, and if you're looking for a library that gives you a more extensive range of color maps than what is provided in tools like Matplotlib, I would encourage you to check out ColorSet. It's got tons of color maps that are perceptually uniform. So essentially, that's a problem with a lot of color maps that Matplotlib has. They have these lines that are perceptually creating separations that are not really in our data, and when we use those color maps in the brain, we might see stuff in the brain that are not actually there. So this would be a package that I recommend using to make your color maps more scientific. Now, with all those being said, let's move to the final bit, which is visualizing neuroimaging specific data. Now, we'll cover a range of tools that help us with that, and I should mention that this tool is by no means, this list of tools is by no means complete. And in the accompanied website, I've put references to articles that try to provide a more exhaustive list of tools. These are just to showcase that these things can be done in a code. code-based environment. So the first step towards making code-based visualizations is to handle your neuroimaging data in a code environment, so basically to load things into memory, and there are tools like Nibabble and DiPy that do that for a Python environment. And it's as simple as, so what you use in a GUI by loading a file is as simple as writing a few lines of code that loads that file into memory. And once you have that file in memory, there are heaps of different visualizations that you could use. So I'm basically going to go over a few example visualizations, show you how these are like used in manuscripts, and then show you examples that these can be made with code. So the first type of visualization is a volume slice rendering. And this is an example of a volume slice rendering, and there are many tools that offer volume slice renders, including Nylearn. In the scripts provided along with these slides, I've given an example that combines Matplotlib with Nibabble to generate volume slice renders. Then the other type of visualization that is commonly used in the field are surface-based visualization, where we basically project information into a cortical surface mesh. This is an example of one of those visualizations, and there are so many different packages, to be honest, that do this. And in the codes that are provided along with the slides, I have given an example where you could make such a figure completely from code. There's also volume to surface transformation. So the idea is you can get a file that is volumetric. It could be an atlas parcellation that is provided in a nifty format. And there are these code-based approaches that essentially make surfaces out of those, and you can get a surface representation of that. There are a few tools that I know that can make these, and I've provided a single example of visualizing this subcortical parcellation atlas with code. The next type of visualization that I've provided examples in the notebook are tractography visualizations. There are a few tools that do it, including Surface and Cerebro. And I have provided a single example of a tool that does it in the code. But anyways, a talk is coming to a close. Just make sure to test the codes that we've provided. You can load it in Google Colab, so you don't even need to install anything on your computer. There's also the option of loading it on Neurodesk that Stefan and his team helped me set up in the past few days, so make sure to check that out. With that, I would like to say that doing open science is not an individual effort. It's usually something supported by the community, and I am privileged that both my current and previous affiliated supervisors have given me the opportunity to spend time on making my science open, and I also got to acknowledge the help that I got from the OHBM and the OSIG community in particular, and Neuro that has supported my personal endeavors in open science. With that, I would like to thank you for listening and open the room for Q&A.